Now we discuss the principle of inclusion-exclusion, and we'll start with the first investigate activity from the textbook, which involves distributing 11 key lime pies to 4 kids. And the goal is eventually to count the number of ways to do it so that no kid gets strictly more than 3 pies, because apparently a kid eating 4 pies is too much, but a kid eating 3 pies is okay. So first let's do the problem with no restrictions at all. Now, as we already saw with stars and bars types of arguments, the answer should be 14 choose 3, because you're counting the number of star and bar charts with 11 stars for the 11 pies and 3 bars for the ways to divide it up into the 4 kids. And then the second question is, how many ways are there to distribute the pies so that at least one child gets more than 3? And of course this is going to be an overcount, but it's an important one that we need to know how to do. So suppose the first kid, which the book decides to name Al, gets at least 4 pies. Well then, if you look at the distribution, it's the number of ways that you could distribute the pie so Al gets at least 4 is the number of solutions to this equation, where A is at least 4. One way to solve this problem is to first give Al those 4 pies and then distribute the remaining 7 among the 4 kids. And the number of ways to do that after you've given out the 4 pies is 7 plus 3 choose 3 for distributing 7 pies among 3 kids. So 10 choose 3. But of course, how many ways can you do it so at least one kid gets at least 4 pies? Well, you have to pick one of those kids in one of 4 ways, and then solve this problem as we did before in 10 choose 3 ways to distribute the remaining pies. And so this is an overcount because obviously there are cases where 2 kids get at least 4 pies, but this is the number of solutions to the problem where at least one kid has gotten more than 4 pies, and you've designated one of the 4 kids that got that number. So part 3 of the investigate activity is to count the number of ways at least 2 of the children get at least 4 pies. And so first let's suppose it's Al and Bruce. Well then, just like this logic, first give Al and Bruce their 4 pies, and then distribute the remaining 3 pies among all 4 children. It's worth pointing out that this is an at least 4 requirement, so they can get more. And so there's 3 pies among 3 children, it's 6 choose 3. And how many ways could we have picked Al and Bruce? Well, 1 way, but how many ways could we have picked 2 kids? 6. So we should multiply this by 6 like we do on the next slide. And so there's 6 ways to pick the 2 kids. And so the number of ways to pick 2 kids and give them too many pies is 6 times 6 choose 3. Now, how about if we want to give 3 kids too many pies? Well, if 3 kids have too many pies, that's 4 plus 4 plus 4. That's 12 pies, which is greater than 11. So there's no way to give 3 kids too many pies. And so back to our original problem, how many ways can we distribute the 11 pies to the 4 kids so that no one gets more than 3? Well, let's take the total number of ways we could distribute the pies, and then let's subtract off the ones where at least one kid got too many. But we found this is an overcount because, for instance, one of these answers counts the ways we gave Al too many, and another one counts the ways we gave Bruce too many, but it's possible we could have given Al and Bruce too many, so there's certain solutions that are counted here twice, once for Al and once from the perspective of Bruce, but are only counted here once. So we need to add them back in, and so that's why we add them. We add back in the solutions where we gave 2 kids too many, because each of those cases was counted twice here and once here, and so it popped up a negative number of times, and so we add it back in. And so this is the principle of inclusion-exclusion, and so this is the answer, and it's just some number from here. And that's basically how inclusion-exclusion works. You start with a problem you know how to solve, and you start subtracting off the overcounting, and then you start adding back in when you undercount, and you go back and forth until eventually you get the answer. To make this problem more explicit, we'll use set theory. In this case, I'm going to actually just use ordinary cardinality symbols from now on. So A is the set of pi distributions, 11 pi's to 4 kids. Let AI be the number, the set of pi distributions where child I gets too much, where too much is at least 4. And so the thing we're really interested in is the size of this set difference, the number of distributions where no kid gets too many. And so we want to throw out this union because any point in this union is a distribution where at least one kid gets too many. But one problem, of course, is that these sets are not disjoint. And so we need to do subtraction first to take care of this set difference. But then we have to add back in the intersections, the pairwise intersections, because these pairwise intersections correspond to cases where 2 kids got too many, and they popped up in both sets, and they're both counted too many times. Once here, and with negative signs, and once here, so we have a negative number of times. So we have to add that back in. And then in general, we have to deal with the fact that we've overcounted some more. Any distribution that pops up in 3 of the sets got counted not enough, or too many times. Once here, 3 times here, and 3 times here. And if you add 1 minus 3 plus 3 is 1, and so we need to subtract them off. And finally, you need to add back in the intersection of all 4. The reason why we didn't see this stuff on the previous slide is because in our case, the intersections here are all empty. As we saw, there's no distribution where 3 kids get at least 4 pi's each. And so these were actually a bunch of zeros. But in general, they might actually pop up. And this is the principle of inclusion-exclusion when you're dealing with 4 sets. And on a later slide, I will actually give the general formula. It's actually quite ugly, which is why the book chooses not to do it at all. But it's worth knowing. So as the next example, I'm going to choose the investigate activity from the textbook involving counting derangements. And the problem is you're going to pull a senior prank by taking the nameplates from 5 professors' doors and switching them so that nobody gets their same name back. And so for this one, I chose the 5 tenure-track professors that were all hired the same time I was, Dr. Kronholm, Dr. Cifuentes, Dr. Suazo, Dr. Vilvert, and myself. And so an obvious overcount is that there's 5 factorial possible ways to rearrange our nameplates outside of our office doors. But obviously this is an overcount because it includes cases like the one where all of us keep our same name. And we want to mix them all up. So this is not good. This is way too much. So let's subtract off cases where one of the professors kept their nameplate. Suppose I keeps their nameplate. Well, then there are 4 factorial possible ways to rearrange the remaining 4 professors' nameplates. And there were 5 ways to pick this professor. And so let's subtract this off. 5 times 4 factorial. Let's subtract off. Hopefully this gets us closer to the answer. And so if you actually look at the list you get, well, for one thing, if you actually calculate this, you see you get 0, which is clearly wrong. But one reason why we get 0 is because we've got an undercount now. We've removed this permutation twice in this difference, but it only appeared once here. Why do we remove it twice? Well, because it appears once in this formula for Dr. Kronholm keeping his nameplate, and it pops up once in this formula for Dr. Cifuentes keeping his nameplate. And so we've undercounted. We need to throw those out. So in order to throw those out, those negative ones out, we need to add them back in, which is what we're going to do next. So suppose 2 of the professors keep their nameplate. Well, there are 3 factorial ways to arrange the remaining nameplates. So for instance, Dr. Kronholm and Dr. Cifuentes. And so there's 5 choose 2 ways to pick I and J. And then there's 3 factorial ways to rearrange the remaining nameplates. And so we add this back into our count. And so this corrects the mistake we had before, because this guy is counted exactly once in this term. And so now it no longer appears. But now we run into a problem that we've got an overcount, because let's consider this permutation where Dr. Cronholm, Cifuentes, and Suazo kept their nameplates, and you guys switched me and Dr. Villaverts. And here the problem is any two of these possible numbers that we see in the first part were counted 3 times here. And if you fix any one of them, it was counted negative 3 times from this term, but it also appeared originally in this term. So you have 1 minus 3 plus 3, which is 1, but this is not a solution to our problem. So we see that it appears once in our supposed count, but it should appear 0 times. And so we need to subtract off these ones as well. And we'll do that in the next slide. So now we suppose 3 of the professors keep their nameplates, I, J, K. Then there's 2 factorial ways to rearrange the remaining 2. And so these are the number of things that we're currently overcounting. So let's throw them out. And so this is now our current answer, where we've got all possible ones. We've removed all permutations where we've selected a particular fixed point. We've added back in all permutations where we've chosen specified 2 fixed points, and now we've subtracted all permutations where we've chosen 3 fixed points. But now we see that this remaining permutation is counted the wrong number of times, the one where everybody keeps their nameplate. It pops up once here, 5 times, once for each time you pick one of these numbers in the second term, 10 times in the third term for any way to pick any 2 of these as fixed points, and then 3 times in this last term for any way to pick 3 of these fixed points. And so it appears negative 4 times in this equation, and it's the only one that is still remaining with the wrong number, because of course generally you also need to pick all the ways you pick 4 fixed points, but once 4 of the terms in the permutation are fixed, the 5th one is fixed too. So we just need to add the 4 back on. And now we have the answer. And so that's inclusion exclusion. Every time we overcount, we subtract off the things we've overcounted by. And then when we undercount, we add back in the things that we've undercounted. And you keep doing this until eventually you get the right number. And it's worth pointing out 5 factorial minus 5 factorial is 0. And 5 choose 3 is the same as 5 choose 2, so I can apply the distributive property. And so then there's just this calculation, and miraculously you end up with 24. Before you hop the gun, in general you do not get n minus 1 factorial as an answer. In fact, it turns out that the correct formula for the number of derangements of n involves summations of negative powers of factorials times binomial coefficients. There actually is no smaller formula. This is, in general, the best we can get.